Welcome. In this session, we will learn how to convert a continuous time signal to a discrete time signal. And this operation is referred as sampling operation. So the goal in this session is to learn how to convert a continuous time signal to a discrete time signal. So our goal here is to learn how to convert a continuous time signal to a discrete time signal. How do we convert a continuous time signal to a discrete time signal? So we'll learn this. Now let's suppose we have a signal time domain. The signal looks like this. So let's suppose x of t is our signal. It varies with time like this. So this is our signal in time domain. Now if I suppose the Fourier transform of this signal is this. So if I let me suppose the Fourier transform of the sequence looks like this. Means the frequency domain representation of the signal is this. So this will be x of omega. How do I obtain x of omega? By taking Fourier transform of this x of t. And let's suppose the frequency domain representation looks like, let me redraw this, and let's suppose this looks like this, and the spectrum varies from minus b to b. Now before I proceed, remember to compute the spectrum of any signal, we only consider positive frequencies. We never consider negative frequencies. Now, negative frequencies are only drawn, means a negative spectrum is drawn only for the mathematical convenience. It has no other purpose in signal processing. So it's drawn only for mathematical convenience or ease. So this is to make the mathematics valid, we use this negative. We draw the negative spectrum also. So to make it mathematically valid, we draw the negative frequency spectrum also. Otherwise, it has no part in computing the spectrum of a signal. So when I have to say the frequency content of the signal, I say the frequency varies from 0 to b, means the maximum frequency component of this signal of this continuous time signal is b. It's b. So the maximum frequency component is b. All right, not 2b, means it does not vary from minus b to plus b. This minus b to 0 is only drawn for mathematical convenience. All right, so this is the spectrum. So whether I say this or this means one are the same thing. This is the time domain representation of the signal, and this is the frequency domain representation of the same signal. So this is the frequency domain representation of the same signal. So this is the frequency domain representation of this signal. So whether I say x of t or x of omega, it means one and the same thing. You must remember. So one is time domain representation, other is frequency domain representation. That's the difference. So that's the difference between the two. All right. So now my aim is to convert this x of t to a discrete time signal. So how do I do that? See, suppose I want to, now discrete time signal means this signal will be defined only at discrete instance of time. Now suppose I want to have the samples like this, means I want to obtain the samples like this. I want to obtain this sample, I want to have this sample, I want to have this sample of the signal, means this value of the signal, sample means this value of the signal, and so on. Same way on negative side, I want to have this sample, and this sample. Now how do I do that mathematically? And let's suppose these samples are obtained at equal time interval, means if this is at 0, this is at 1 time interval, this is at 2nd time interval, 3rd time interval, and so on. And this is called the sampling time, means we obtain the values at equal sampling time, means at which we obtain the samples of the x of t. That's referred as sampling time. How do I obtain this operation? How do I perform mathematically this operation? Now mathematically I can perform it like this. If I say I have another signal or sequence, means if I have another signal or sequence that is p of t, let's suppose this is my another sequence where is like this. So but the sequence, the signal has values like this. So the values of this signal are like this. So it's 1 at 0 at TS, at 2TS, at 3TS. Now what's meant by TS? TS is the sampling time at which I want to sample this signal. So TS is the sampling time at which I want to sample this. And this is called actually uniform sampling in signal processing. This or in communication, this is referred as uniform sampling. So I'm obtaining the samples of this signal at 0, at TS, at 2TS, whatever is the value of TS. So the value of TS can be anything, 1 millisecond, 1 microsecond, or 1 nanosecond, whatever is the value of TS, or even 1 second. All right, so, but I'm obtaining at an equal duration, means I'm obtaining the samples at uniformly at equal time. All right, so this is how I can obtain. So if I multiply this x of t with p of t, what will happen? You can obtain the samples. You can see now, see this signal is 0 between these, and you have a value of the signal only at 0 at TS, at 2TS, and it is 0 at other instance. And you can do the sampling of x of t by multiplying it with p of t, by multiplying it with p of t. So mathematically, we can do the operation by multiplying p of t with x of t, and let's call the output operation as x of t. So s of t is the multiplication of p of t. That is the impulse train. This is referred as impulse train. This is the impulse train, and we can obtain the samples of x of t by multiplying with this p of t. So what we'll have a signal that looks like this. So the output signal looks like this. So t, this is x of t. Let me draw the values. So the values are 0. I'm not drawing these values to the scale. Please draw it yourself. You can, I'm drawing a rough values here. So these are the values, and so on, and so these are the samples of this. So this will be s of t, which is equal to the multiplication of s of t with p of t. So this is at 0, this is at TS, this is at 2TS, this is at 3TS, and so on, 4TS, 5TS, and so on. This is at minus TS, this is at minus 2TS. So this is how I accomplished the operation of the sampling of x of t by multiplying it with another signal, that's p of t, and the output is the sampled signal, which looks like the sampled version of the original signal. So this is our sequence. So this is our discrete time version of the same signal. And now it is only defined at these instants of time. It is defined only at these instants of time. So mathematically, how do we write p of t first of all? If I say mathematically this, what is this equal? P of t, you can say, looks like an impulse train, and you can write it like this. You can say this is n going from minus infinity to infinity delta t minus mts. So mathematically we can write it like this. Now when you multiply x of t with p of t, and that we name it as s of t, mathematically it looks like you are doing this operation. So this is multiplying n with minus infinity delta t minus mts. If you expand it, it will look like this. Please remember that. This is simply the impulse train. If you expand it, you can expand it. You can say this is, if I say n varies from minus infinity, and let me start substituting values from minus 2. So this will be t plus 2ts, t plus ts when n is minus 1, plus when n is 0, this will be delta t. So this is delta t plus minus, this is minus ts plus delta t minus 2ts when n is 2. So you can see, well, the signal is simply delta t minus this sample, delta t minus ts minus this sample minus shifted version of this, delta t plus ts minus this sample, delta t plus 2s minus this sample, delta t minus 2ts minus this sample, and so on. You can repeat it for negative and positive value. So this is an impulse train. So this is simply an impulse train. Now when you multiply this impulse train with the given signal, means the input signal, what will happen? Mathematically, it looks like you are doing this operation. So you are multiplying x of t with delta t minus ts. So this operation, what's this equal to? You can write it like this, minus infinity to infinity. This is same as x of nts delta t minus nt. So what you are obtaining the samples of x of t at instance nts. N is varying from 1, 0, 1, 2, 3 up to infinity, and from minus 1 to minus infinity. So you obtain the samples of this. You can check it. You obtain the samples of x of t at these time instants. Now, so one sample of this. So when I multiply x of t with delta t minus nts, one sample of this, I can obtain that. So I say this is nts delta t minus nts. So this is delta t minus nts, and we often drop the nts from this. So we often drop it like this, and we write it delta. Sorry. So we write it like this. We say this is delta t minus. So we often drop this and this ts from this notation, and we write it only x of n delta t minus nt. So we often drop the ts. We know this is done at uniformly, and the sampling is done at uniform sampling rate. So we drop ts, and we sometimes write it simply x of. This is the meaning. So this is the discrete version of the sequence, original sequence. So this is the discrete version of the original sequence. So this is just the notation part. Please remember it. So this is one sample value of x of t. So this is one sample of an nth sample, and can be anything 0, 1, 2, 3, or minus 1, minus 2, and so on. So this is one sample of that sequence. So this is nth sample of that x of t. So this is how we sample a discrete time, continuous time signal. So this is how we obtain the samples or sample a continuous time signal and convert it into discrete time. I hope you understood this. So the result of this mathematical operation is the multiplication between this p of t, which is the impulse train, and this x of t gives us the discrete version of this x of t, means the sampled version of t. So this is the operation in time domain. Now if I go to the frequency domain, what is going on? So this is what you are doing in time domain. Now simultaneously, what's happening in the frequency domain? As soon as when you perform this multiplication operation, what are you doing in frequency domain? All right, so when you multiplied x of t with p of t, so and we obtain s of t. Now I said if two signals in the in earlier session, I said if two signals are multiplied in one domain, they will be convolved in the frequency domain or other domain. See here, the signals are multiplied. So in the frequency domain, these will be convolved. As these signals are multiplied in time domain, so the signals will be convolved in the frequency domain. So if I say s of omega, means the frequency domain representation of s of t is simply the convolution between x of omega, where x of omega is the Fourier transform of x of t, and this is the convolution operation with p of omega. So that's what you are doing in frequency domain. So when you multiply x of t with p of t, it means you are convolving the signals in frequency domain. What's this 1 by 2? 1 by 2 is simply a scaling constant. This has nothing to do with this convolution operation. So this is simply a scaling operation there, because we are using omega as the unit. So that's why 1 by 2 is there. All right. So this is what you are performing in frequency domain. Now, if I substitute the x of omega, my x of omega is already given, that's this, so our x of omega is this. Now, what's P of omega? P of omega is the Fourier transform of this impulse train. And if you see, P of omega means the Fourier transform of P of t Fourier transform of P of t, that will be simply 2 pi by Ts. Ts is the sampling time. Let's rewrite it. So this means Fourier transform of summation n running from minus infinity to infinity delta t minus nts. So this is the Fourier transform of this signal. The Fourier transform of this signal is simply, remember, it is this impulse train, same impulse train. So in frequency domain, the representation of the impulse train is again an impulse train. I'm using now K to separate that, to show that this is the frequency domain representation and this is the time domain representation. K is running from minus infinity. You can use N also, so there is no issue in that. So the Fourier transform of delta t minus nts means the impulse train that runs from minus infinity to plus infinity is again an impulse train in frequency domain. And there is a scaling constant 2 pi by ts. Where does this 2 pi come from? Now, what's the relationship between omega s and t? Omega s is the sampling frequency, and the unit is radians per second. That's the relationship between omega s and ts. So when you obtain the Fourier transform of this, the Fourier transform of this is this. So again, this is an impulse train, and if I plot it, so this is again an impulse train in frequency domain. So this is the impulse train, and you can say this is P of omega. So this is phi of omega, and P of omega in frequency domain is again an impulse train. And this is 0, this is omega s, this is twice omega s, and this is 3 omega s. And same way you have an impulse at minus omega s, minus twice omega s, and so on. So the Fourier representation or the frequency domain representation of this impulse train is again an impulse train, and the amplitude is 2 pi by ts. You can see the amplitude is 2 pi by ts. So the amplitude of these impulses is 2 pi by ts. All right, so the frequency domain representation of the impulse train in time domain is again a impulse train in frequency domain. Impulse train means simply it's varying from minus infinity to infinity. So it means the Fourier transform is again are impulses. Means the frequency domain representation are again impulses. So what you are doing, you are actually convolving this impulse train with this. So you are convolving impulse train with this. That's what you are doing. So if I say, if I redraw these, so my s of omega is simply 2 pi. Sorry, there is 1 by 2 pi, not 2 pi. 1 by 2 pi. Where is that? This 1 by 2 pi x of omega convolution with P of omega. If I substitute the value of P of omega is this, be 1 by 2 pi x of omega convolution with 2 pi by ts summation running from k minus infinity to infinity delta omega minus k omega s. So this is the frequency domain representation of the signal. Now 2 pi and 2 pi will cancel, and let me write 1 by ts outside. This will be x of omega convolution with star minus convolution minus infinity to infinity delta omega minus k omega s. Now if I take this x of omega inside this summation, so this will be 1 by Ts summation k running from minus to infinity x of omega convolution with delta omega minus k omega. So next what we are doing, so this is the convolution between this and this. If you remember, I said convolution of any sequence means the first operation with delta is the sequence itself or the signal itself. Convolution of delta with x of omega, delta omega with x of omega. And same way, convolution of x of omega with delta omega minus k omega s will be simply replace omega by omega minus k omega. So this will be the convolution between these two. So this is the convolution. And if you substitute it here, s of omega will simply be 1 by Ts summation k running from minus infinity to infinity x of omega minus k omega s. So this is what you are doing in frequency domain. So this is what is happening in frequency domain. So when you convolve this p of omega with this spectrum, we obtain an expression that looks like this. Now what's this expression? If I expand this expression, let me expand it. So this is 1 by Ts, and let's start substituting the values of k. And let's say k is minus 2. So this will be x of omega plus omega s twice omega s, x of omega plus omega s when k is minus 1 plus x of omega plus x of omega minus omega s when k is 1, x of omega minus twice omega s when k is 2, and so on, and so on. So when you multiply a signal with impulse train, you obtain the samples of that signal. Now in frequency domain, what's happening in the frequency domain? So when you convolve a signal, and the spectrum of a signal with the impulse train, you obtain a spectrum that looks like this. Now let's interpret what is the meaning of this. This is simply saying the Fourier transform of the sampled signal, means the spectrum of the sampled signal is given by an infinite sum of shifted version of the original Fourier transform or original spectrum. So the spectrum of the sampled signal, means the spectrum of sampled signal is simply the infinite sum of shifted versions of the original spectrum or original Fourier original spectrum, original signal spectrum. So the spectrum of the sampled signal is simply the infinite sum of the shifted versions of x of omega. You can see x of omega, this means the shifted version of x of omega towards the right, means now the as it is shifted towards this at omega s, and this is the shifted version of x of omega, and the shift will means it will be symmetrical across twice omega s. Same way, this means the shifted version of x of omega, and it means towards the left, and this means the shift means the spectrum will now be at, means it will be identical with x of omega, but that shift is at omega s, and this is at minus omega s, and this is at minus twice omega s. So simply you can say the spectrum of the shift in this sampled signal is simply an infinite sum of the shifted version of the original signal spectrum or original Fourier transform. So let's draw it. If the Fourier transform of the spectrum of the original signal, we have already drawn it. and we assume it looks like this. X of omega is looks like this, and it is varying from minus b to b, means it is non-zero between minus b to b, and rest of the this values of frequency components are 0. So this is our x of omega. So this is our x of omega part. But what's the output of s of omega? S of omega is simply an infinite sum. So if I draw it, and if I draw the spectrum, so what I have to draw? I have to draw the infinite versions of the same x of omega. Now to draw it, we'll have three cases. We'll discuss three cases. Means when omega s is equal to, when omega s is, let us suppose when omega s is greater than twice b, where b is the maximum frequency component. Same way when omega s is equal to twice b, means exactly equal to the twice b. And third case that we shall discuss is when omega s is less than twice b. Now let's take an example for this thrice omega. Sorry, not omega, 3b, means 3 times the maximum frequency component. And this is the same as when equal. And let's take the case 3 by 2b, means when the omega s is 1.5 times the maximum frequency component. Let's see how will the spectrum of the signal look. Spectrum of the sampled signal I'm talking about. This is the spectrum of the original signal. This is the spectrum of the original signal. Now you can see the spectrum has an infinite sum. The spectrum of the sampled signal is the infinite sum of the shifted versions of the original signal spectrum. So let's try it. Let's plot it for these three cases. Let me take the first case and let's plot it. So I say this is the frequency axis, and this is our s of omega. Now the amplitude of each of these shifted version is 1 by ts. So this is the spectrum. So the first part of this is x of omega. So we'll have x of omega as it is. So this is our x of omega. Again, I'm not drawing these values to the scale. Please check it yourself. So this is when this is at 0, and this is our omega axis. And suppose this is omega s value. This is twice omega s, and so on. Same way, suppose this is minus omega s, and this is minus twice omega s. This value of omega is minus twice omega s. So now my omega s is 3 times b, means the maximum frequency component. So this will occur somewhere here. So you can say this is this part of the spectrum. So now this is this part of the spectrum. So this is here, and the amplitude of each, means the maximum amplitude is 1 by ts. This has also maximum amplitude equal to 1 by ts. Same way I can draw the, let me shift the value towards here. So this is twice omega s. So this, all right. Same way so this is this part of the spectrum. So this is the shifted version, this shifted version, and it is shifted at twice omega s. This is shifted at omega s. You can check it. It is the identical spectrum, but it is shifted at 0 omega s, twice omega s, thrice omega s, so on. So this will repeat continuously towards omega going towards plus infinity. Same way I can draw the same spectrum. This is when shifted at minus omega s. So this is this part. So I'm drawing this part. So this is the shifted version of x of omega at minus omega. And let me shift to the minus twice omega s over here. So this is minus twice omega s, and this is in this part, and so on. So you can draw the rest of the components yourself. And this is 1 by ts, means the maximum amplitude is 1 by ts. All right. So this is the spectrum of the sampled signal. All right. You can see now. Before I proceed to the next case, what is this? How much is this? How much is this value? If this is b, this is omega s. How much will be this? This will be, see, the difference between this and this is B. So this will be, if this is omega s, so this will be omega s minus B, right? Or you can say this is 2B here. For this case, this is 2B. So this is 2B. This is 2B because omega s is 3B. So 3B minus B is 2B. Same way, what is this? This will be 4B. Or you can say this is omega s plus B. Same way you can see the this other frequency components, means this what are these frequency components, what is this frequency component, what is this frequency component. So all right, so for this special case, means when omega s is 3B, and remember omega s, the relationship between the omega s and this ts. Ts is the time at which you sampled the signal. So what should this omega s give you? Omega s is the relationship between omega s and this is 2 pi, so you can say this is 1 by ts. So ts is sampling time, fs is the sampling frequency, means the rate at which you are sampling the this in this time and the signal, means the time domain signal. Now let's plot it for the second case, means when omega s is exactly equal to 2b. So let's draw this for the second case. One more time, I'm not drawing these values using a scale, so you can check it yourself. Now this is s of omega when omega s is exactly equal to 2b, when omega s is 2b. So the first component I have to draw is x of omega, so this will be identical. So x, so this will be same, that is given to us in the original, and the maximum amplitude is 1 by ts. Now if this is b and this is our omega s, so this is omega s, and so this is twice omega s, so this is 3 omega s, and so on. So this is our omega axis, and this is minus omega s, and this is minus twice omega s, and so on. Now to draw this part, when omega s is 2b, this is the shifted version of simply this. So this will look like this. Now here these two touch each other, so the frequency components will touch each other, meaning the shifted versions will touch each other. So this is omega, x of omega minus twice omega. So this is the second part. Same way you can draw the third part. So you can say this is x of omega minus 3 omega, and the amplitude of each maximum amplitude is equal. All right. So how much is this? This omega s is 2b, this will be 3b, and so on. Same way I can repeat the same thing on negative side. So this is, please remember these will touch this time. So this is minus b, and to draw it for this, so this will be simply x of omega plus twice omega. This is x of omega plus omega. This is x of omega plus twice omega. All right, so this is when omega s is 2b. So you can see the spectra touch each other now. So they touch at b. Now third case is when omega s is, so the third case is when omega s is equal to 3 by 2 b, and this is the same case when omega is less than 2b, when omega is less than 2b. So we are discussing this case under this. All right, so this is the third case. All right, so if I plot this for this case, so if I draw it for this, so this is our s of omega, this is omega, and this is 0. Let's suppose this is omega, this part is how much? So if I say this is omega s, this is omega here twice omega s, and this is twice omega s, and same way on the negative side, this will be minus omega s, this will be minus twice omega s. So now you can plot the values for this. So first let me draw it. It is simply the same spectrum. So it will be simply x of omega. You can check it. All right. So we draw this. So this will be simply, suppose to this. So this will go to this. This is long again. So we can write like, all right. So marker today. All right, so this is the original x of omega. So this is 1 by ts. Now the shifted version is x of omega minus omega s. You can see the spectra will touch each other now. Means they will overlap, the spectras overlap. And same way if you draw it for this, and if you draw it for this, you can see the spectrums overlap each other. So in this third case, the spectra will touch each other because this is, if this is B, a different marker. So if this is B, so this is the same span, this is minus B. So this is actually, if this is omega s, how much is this? This is omega s minus B. So if this is omega s is simply 3 by 2. 3 by 2 means this should be exactly at half. So this will be exactly at half. So this will be 1 by 2b. So this is half of b. Same way you can calculate the other values. And if I repeat this on the negative side as well, this will touch out this, and this will touch out this end. So you can see the spectrum is overlap when in the third case. So these spectrums will overlap with each other, and the maximum amplitude of each spectra is 1 by t. So this is the plot of S of omega, means the spectrum of the sampled signal for 3 different cases. Please check it, please draw it again and again, you will get the idea. Now one important observation from this, you must remember it for Fourier transform. Very important observation is this. This is very, very important point. Have a look at the spectrum of the continuous time signal. It is continuous in nature. The spectrum is continuous in nature. Now have a look at the spectrum of the discrete sampled signal, discrete time signal. It is simply exactly the same spectrum which is replicated at omega s, at different omega s. So the spectrum of the discrete time signal is also continuous. So the spectrum is also continuous. So the spectrum of sampled signal is also continuous. Sampled signal spectrum is continuous in nature. Continuous. But it is with respect to omega. You must remember it is with respect to omega. It is continuously varying. It's not discrete. It is so the sampled spectrum is also continuous. So if the input spectrum is continuous, the sampled spectrum is also continuous. Sampled signal spectrum is also continuous. This is very, very important property. You must remember this. You must remember this very important observation. So whatever is the spectrum of the continuous time signal, the spectrum of the discrete time or the sampled signal is again continuous, the same. All right, so please plot it for 3 different cases. Let me stop here. In the next session, what we are going to do, we are going to see how do we reconstruct our signal from this. How do we reconstruct our signal from this? If this is the time domain form, or this, if this is the frequency domain form. So how do we reconstruct? And we'll see it for these 3 different cases. So see the spectrum of this condition to recover the signal for these three different. Please plot it again and again for these three different to get an idea what's happening to what is meant by omega s and what is the implication of this in omega s. Please check it for these three different cases, and this will give you an important observation in the relationship between the maximum frequency component means B and omega. How you should use these. This is very important for this analysis. All right, let me end it here. In the next session, we'll see the reconstruction.